So if we were to summarize the results of our study, we would say there are three conclusions that some would consider almost paradoxical the way they sound. The first is that in a deeply decarbonized energy system, there is a big change in the physical energy system as illustrated by those Sankey diagrams I showed you. The types of energy, what flows through the system is very different, and yet there's very little change in the energy services that are provided. We can get around, we can cook our food, we can light and heat and cool our houses and remain in comfort in that system. Secondly, in a deeply decarbonized energy economy, there's a big change in the energy economy because we're spending a whole lot less on fossil fuels and we're spending a whole lot more on clean technologies. We're creating an energy system that goes from one that's based on the price of a barrel of oil to one that's based on the price of things like solar panels, electric vehicles, highly efficient boilers, and so forth. The second conclusion of our report is that deep decarbonization cost is affordable. So the net cost of providing energy services, that is, the sources of energy and the way that we use energy, is a little less than 1% of GDP more than at present, with a pretty wide uncertainty range. It could be negative cost, meaning that if things go in a certain direction and the costs are greatly improved, for example, by large scale and global markets that drive down cost, we'll actually be saving money compared to the high fossil fuel system of the future, even if we use the conservative assumptions that we did in our analysis. The net cost is not very large. And in none of this did we include the economic benefits of avoided pollution or climate change. If you include those, deep decarbonization is a clear winner, but that's a separate piece of analysis. And so that net cost is relatively low. And since that cost is relatively low, what consumers see as their cost is also relatively low and might even be a win when these technologies costs come down. Finally, from the standpoint of the macroeconomy, the 1% change is a small net cost relative to GDP. We currently spend 6 or 7% of GDP on energy in the United States. So it's not a large change compared to what we already do, but there's significant benefits for the macroeconomy. One of those is that historically, rapid oil price spikes have led to prolonged economic woes in this country. When you reduce oil consumption to well below 1% of GDP, which you do under deep decarbonization, you are no longer vulnerable to those sorts of price spikes. That is a huge impact when you look back over time and see how much unemployment and human misery is caused by the consequences of oil price spikes. This figure shows the transition of both the supply and the demand side of the energy system for the high renewables scenario. And what you see across the top is energy demand by sector. What you see across the middle is energy supply. And what you see across the bottom is the carbon intensity, those black lines of the different fuels. Now, across the top, you see liquid fuels, gas fuels, and electricity. So what we're seeing is, over time, the change in where energy gets used and what it gets used for. And I want to point out a couple things, but let's look at the middle row, energy supply, the right-hand side, electricity. And what you see is a approximate doubling of electricity supply between 2014, current, and 2050. And that's because you're using a great deal of electricity to substitute for things that used to use fossil fuels. If we look at that figure in the middle row on the right-hand side, where does the electricity itself come from in a high renewables case? Well, you can see blue and yellow, that's solar and wind. And then you can see nuclear. The share of nuclear is about the same as it is today. It says that fleet is maintained. And then you see hydroelectric. And then you see the gray, which is the dominant part of today's generation, which is fossil fuels, becoming a very, very small share. If you look below that figure to the black line, you can see that indeed the carbon intensity of electricity has been reduced by a factor of about 35 relative to today. That's how we do it. Solar, wind, in some cases with nuclear, in some cases with carbon capture and storage. But in all of those cases, you're able to build a reliable electricity system bigger than the one today that provides for the majority of our end uses. The other thing that I want to point out, if you look at the slide on the left-hand side in the middle row, that's liquid fuels. Well, our liquid fuels are dominated by petroleum today, which is the brown. And what you see is that liquid fuels go way down because basically we are electrifying the transportation uses that currently use so much petroleum. And so it's a decrease by a factor of about 5 relative today. And what you see also is a little bit of increase in the use of hydrogen for fuel cell vehicles. Finally, in the middle row and the middle column, you see a big green wedge under gas fuels. And what's happening in this scenario is the use of biomass resources to gasify so that you can put them into the natural gas pipeline we have today and have a combustion fuel for end uses that are difficult to electrify that has much lower carbon. Again, if you look in the third row beneath that in the middle, you'll see that the carbon intensity has gone down by a factor of 5 to a level that we can tolerate and still do some combustion. We maintain our gas supply infrastructure. We don't have to get rid of the pipeline, but instead of fossil natural gas, we're putting renewable natural gas into it. These are the kinds of tricks that we can do. I call them tricks, but these are basically a sustained infrastructure transformation that takes place year by year over several decades that allow us to get to deep decarbonization without great disruption of our economy, without any disruption of our economy.